Alrighty, well, it's 4:32, so I think we will get started. Can everyone hear me okay? Yes, thumbs up. Okay, great. Well, thank you all for joining us this afternoon for a presentation from my colleagues at our firm, FB Environmental, on the Megunticook River, and really an introduction to river ecology, but particularly talking about the Megunticook River. So for those that don't know me, my name is Maggie. I am a scientist at FB Environmental, and I have been assisting the Megunticook River Citizens Advisory Committee with their charge to engage the community in exploring resiliency outcomes for the Megunticook River as the project moves forward. So this is the first presentation that we're hosting and what we expect to be a monthly series of presentations that will all be held virtually on the third Tuesday of the month at this time. So 1 hour, 4:30 to 5:30. And really our hope is that these presentations can each focus on a different aspect of the river to help both the committee and the public better understand any future management options that are explored for the river. So this is really a way to bring experts in on different topics that we'll work with the committee on scheduling each month to learn about their varying subjects. So the way this is going to go is that we'll begin with a 20 or so minute introductory presentation. This week it's by my colleagues Laura and Luke, who are joining us. And it will then be followed by an opportunity for both the committee to ask questions as well as taking questions from the public. So before we get started, I just wanted to share a few housekeeping notes. I'll just reiterate that we're going to keep the presentation to an hour, so you can expect that between the presentation and questions that we will be done at 5:30. As you can see here, anyone attending that is on the committee is elevated in the webinar to a panel member. So they have a little video and they can unmute their microphones. So we'll have the 20 or so minute presentation. And then after that, the committee members will have a chance to ask any questions that they have. No pressure to ask a question, just an opportunity. You can either use the raise hand feature and unmute your mic, or, and I'm speaking to the committee right now, or you can submit your questions through the Q&A feature and we can read them aloud. And you can submit those questions either with your name or anonymously. And just another note for the committee members, you're all, as panelists, if you unmute your mic, we're all going to hear it. So please keep your microphone muted for the duration of the presentation and at any time that you're not actively speaking. And then following any questions that we get from the committee, my colleague Bina, who is on the screen here, will guide us through any public questions and comments submitted through the Q&A feature. Please be sure those go through Q&A and not the chat feature. We'll then record, or we will record all of the questions that come in through the Q&A, just in case we don't have time to get to them by 5:30. And then we'll work to answer them offline and post them to the town's project webpage. Just another note, the presentation will be live streamed to the town YouTube page, so you should be able to go back and rewatch it there. And we've also enabled the closed caption features for anyone who would like to turn that feature on. We did have a panel memberess try it out, so it sounds like it works. You just need to enable it on your end if you want it. And so I think that's all the housekeeping things that I have to get us started. And I'm now going to turn it over to my colleagues, Laura and Luke, who will give a more thorough introduction to their roles. So take it away.
Perfect. Thank you, Maggie. I'm assuming everyone can see the screen I just shared. Great. So as Maggie said tonight, we'd like to give you a broad introduction to river ecology in the context of the Megunticook River and why it's so important to monitor and protect. But first, I just wanted to introduce myself. and Luke, since we're new faces to this group. So my name is Laura Deemer. I am a senior project manager and environmental monitoring lead at FB Environmental. I manage our water quality monitoring and watershed planning projects across New England for a variety of environments, ranging from inland freshwater lakes and rivers to coastal estuaries and beaches. I'm also a certified lake manager through the North American Lake Management Society, otherwise known as NOMS. And a good portion of my work involves developing and carrying out monitoring, modeling, and restoration efforts for lakes, particularly in Maine and New Hampshire. But my educational background started me with rivers and understanding the biogeochemistry of rivers and streams in response to stressors. My master's work at the University of New Hampshire took me to Siberia in Russia to study the impact of natural forest fires and melting permafrost on nutrient cycling in rivers. So my part in this overall project, I've been managing the Megunticook River monitoring project that took place this fall. Luke performed the field work with assistance from another staff member, Magdalene Kozelik, and you'll be seeing a brief report on that work from us very soon. And I'll let Luke introduce himself.
Hi, everyone. I'm Luke Frankel. I'm a project manager here at FB Environmental. My education background, I got a BA in Earth and Oceanographic Science from Bowdoin College down the coast from Camden. And then I also got a master's in marine science from the Virginia Institute of Marine Science. And my master's research focused on evaluating the impact that nutrient management actions had on water quality in the Chesapeake Bay. They've been undergoing a 40-year restoration effort. And through my master's research, I worked closely with state and federal partners with that work. And then also as a research background, I've done satellite remote sensing research in the Gulf of Maine and also in the Mid-Atlantic Bight as an undergrad, and we're looking at ecosystem change in the ocean. So, and at FB Environmental, I manage numerous water quality monitoring projects in Maine and New Hampshire, especially multiple projects in the coastal region. And like Laura mentioned, I helped with the field work and the data analysis related to the Megunticook River monitoring that we did.
Great, thanks, Luke. So I wanted to start with the basics of watershed science. So what exactly is a watershed and why is it important? A watershed is essentially the area of land that channels rainfall and snowmelt via streams, rivers, ditches, storm drains, and groundwater to a single point, whether that's to a lake, to a river outlet, to the ocean, wherever you define that endpoint. And watersheds really supply the water that replenishes surface waters. So rain that falls down on the land either soaks into the ground or runs off to surface waters. When it's in the ground, water can be taken up by plants or seep into groundwater and run off to surface waters. Water can then evaporate from surface waters or plants back into the atmosphere to then later fall as rain again in this never-ending loop known as the water cycle. So this water also carries with it nutrients and organic matter that's critical to supporting life and the ecology of both land and water environments. So here is the watershed area for the Megunticook River, shown in the red outline. The watershed covers 31 square miles. All the rain that falls in this area eventually makes its way to all the feeder tributaries that enter Megunticook Lake, that then feed into the Megunticook River, which then outlets to Camden Harbor and the ocean. So whatever the water picks up along the way is also being carried into these water systems. In undeveloped watersheds, the riverine system is a dynamic and interconnected place supporting a diversity of species, whether that's from tiny plankton and invertebrates to fish and birds to mammals. Each of these species relies on the other within this intricate food web so that the health of one supports all others in this balanced ecosystem. The riparian buffer that you see here represents a healthy riparian buffer in that it's a multi-storied tree canopy that helps to intercept and infiltrate rainfall, filters nutrients, and provides important shade cover for maintaining cooler air and water temperatures for some sensitive species. The vegetation in that buffer drops in leaves and other woody material into river systems, creating diverse habitats for a multitude of aquatic species. And within the river itself, the algae and plants are eaten by zooplankton, which are eaten by macroinvertebrates like caddisflies, which are eaten by small fish, which are then often eaten by larger fish or even birds and mammals. And when one of these links in the food web is disrupted, it sends a cascading effect through the entire system. So for example, a loss in habitat in the river could reduce the population of macroinvertebrates, which would reduce the fish population. And without fish, birds of prey may seek new territories. In developed watersheds, forest land that once soaked up rainfall and stabilized soils has now been cleared for our homes, driveways, and roads. So instead of soaking up the rain, these impervious surfaces concentrate runoff in channelized flows that erode nutrient-laden sediments and other pollutants into surface waters, where they can degrade water quality, damage critical habitat, and ultimately upset the natural balance of these ecosystems. Our activities often embed habitats with fill and other materials, removes the natural filtering ability of riparian buffers, and increase the amount of nutrients and other pollutants entering these waters. And this often promotes what homogenized habitats with aquatic vegetation, oftentimes invasive, smothering these nearshore areas, which can reduce populations of critical zooplankton or macroinvertebrates, which then can allow algae to flourish and bloom. Fish species can decline as a result of that. Bird species can decline with that as well. Larger mammals are often moving out to more rural areas. So what we have left is an ecosystem that is much less resilient and often unable to support life in the way that it historically could. So watershed is important because it defines the area impacting the river. It defines where the sources of pollutants are coming from. Taking a look at land cover can tell us a great deal about water quality and habitat conditions impacting the ecological health of the river. So this is a view of the Megunticook River watershed from the north and looking south toward the ocean, which you can see in the background here. The upper watershed area is mostly forested with some rural, residential, and agricultural development. And this view is of the Megunticook River watershed from the south, looking back to the north where we were just looking. So here is Mount Megunticook to the east and Bald Mountain to the west, with Route 1 skirting the southern edge of the watershed down here. So this southern portion of the watershed is much more heavily developed around downtown Camden. This area is dominated by impervious surfaces from our roads, driveways, walkways, residential and commercial buildings, particularly as we move closer to the river's outlet. And these impervious surfaces collect and carry pollutants in stormwater to the river. The area is also serviced by septic systems and sewer, which may represent another potential source of pollutants to groundwater that would ultimately connect with the river. So rivers are not only impacted by their watersheds, but also by in-river alterations by humans. Natural rivers tend to meander and accumulate woody debris to slow the velocity of flow. This creates natural riffle pool patterns and areas where sediment can deposit, such as sand and gravel bars, and which slows that rate of sediment transport downstream. Many of our impacted rivers have been straightened to accommodate development. So channel straightening decreases the total length of the channel and increases that channel slope, generating much higher velocity flows that can scour out banks. So because of this, most straightened channels have armored banks to prevent erosion and force the river to maintain in place. Often habitat diversity is lost, sedimentation downstream is enhanced, and floodplain connection can be limited. This picture shows a small channelized section and armored section of the Megunticook River just downstream of Rawson Ave. And as another example of an in-river alteration by humans, so dams are barriers along rivers that trap water upstream. The river expands as water floods into surrounding areas, both laterally and upstream to an elevation that matches the dam, creating what we call an impoundment. So this impoundment slows down water, it traps sediment and other pollutants behind the dam, which are concentrated in sediment over time. Dissolved oxygen needed for many sensitive species is often reduced in the impounded area, and migratory fish are unable to access areas upstream of the dam. So what happens is this natural exchange of nutrients and organic matter along with organisms such as fish is significantly reduced. So the natural resiliency of the river system is greatly diminished over time. So I'll pass it to Luke, who will now discuss what we monitored this fall in the river.
Great, thanks, Laura. So yeah, as Laura mentioned, we did some monitoring, the first monitoring of our work in the Megunticook River this past fall. And so for the monitoring that we did in the fall, our objective was to initiate one component of a monitoring plan that will establish the baseline condition of the Megunticook River watershed. And so in order to do that, we selected a few sites along the river that represented the various geomorphic conditions within the river. So we picked some sites that represented impoundment sections, also some sites that represented free-flowing areas, and also areas that were different depths within the river. So we can go to the next slide. So just taking a look here on the left, we have a map of the Megunticook River watershed, the lower watershed where the river runs. And you can see in the top left or across the map, we have 7 different sites indicated by the red stars. And so in the top left, we have the East Dam site that we monitored, and that is just below East Dam, which is the beginning of the Megunticook River, just below the outlet of Megunticook Lake. And then at the other end of the impoundment there, we have the second station, which is Seabright Dam, which is just in the impoundment upstream of Seabright Dam. And then moving along to the next site is Powder Mill Dam Ruins, which is a ruins of a former dam that's located a little downstream of Seabright Dam. And then next is a site by the bridge that crosses over on Rawson Ave, that crosses over the river. It's the bridge that's out of, it's closed currently. And so we deployed a logger there because that represents a free-flowing condition part of the river. And then down within kind of more the city proper of Camden, we have 3 sites each located upstream of the 3 dams located within the city center town, or the town center of Camden. And so the first one is Knowlton Street, which is above the Knowlton Street Dam, then Knox Mills Dam, which is above that dam, and then finally the Megunticook site, which is located just upstream of Megunticook Dam in Camden. And so we'll go to the next slide, where we're gonna kind of investigate the different sites more closely with some photos. So if we zoom in the upper watershed, we can see that in East Dam, the site that where we deployed our instruments is just below East Dam. And if we show the photos there, you can see that the instruments that we deployed are in this PVC housing that is located in the bottom of the photo. And then at the top of the photo, you can see that's where East Dam is. And so the instruments we deployed at this site, it's only about 2 feet deep in the stream, in the river there. So the instruments are within a PVC housing that is attached to a cinder block that anchors it to the bottom of the river. And then a steel cable attaches that to further secure it to the shoreline and an adjacent tree. And so if we look at now the sites located more downstream, here we are going to show the 2 sites, the Seabright Dam site, which is located in, again, the impoundment just upstream of Seabright Dam, and then the Powder Mill Dam ruins, which is located near the ruins there. So the top 2 photos show the Seabright Dam. And so at this site, if you look on the photo in the top left, you can see that we have buoys deployed there, which I'll get into detail in a few minutes about the buoy deployment that we used. But this site at Seabright Dam is about 15 feet deep. And so you can see that's what the impoundment, the photo on the top right shows what the impoundment looks like upstream of the buoys. And then in the top left, you can see kind of the dam. It's located about 100 yards upstream of the dam. And then the Powder Mill Dam ruins, you can see the photo on the bottom left shows what the ruins, the dam ruins look like currently. And in the bottom right, there's a photo of me deploying, again, a similar cinder block PVC housing for the instruments that we deployed. And the depth in this smaller impoundment upstream of the dam ruins is about 3 feet deep. So now going to the next slide, we're going to take a look at the Rawson Ave site, which is kind of the free-flowing location along the river. So it is, again, where that bridge is currently closed that crosses the river on Rawson Ave. And you can see this site is, again, about 2 feet deep. It's another shallow site. And in the photo in the top right, again, the instruments we deployed are housed in the PVC cinder block housing. And then the photo on the left just shows kind of an upstream view of the natural section of the river draining to that site. And so now finally, we're going to take a look at the 3 sites located within the town of Camden. The Knowlton Street Dam, the Knox Mill Dam, and Montgomery Dam, which are each located in the impoundments just upstream of the respective dams. So the top left, the Knowlton Street site, you can see that we use the buoy system to deploy our instruments, and that site there is about 8 feet deep. And then again at Knox Mill Dam, we deployed the buoys as well, and that site is about 12 feet deep. And then finally, in the bottom right, you can see Montgomery Dam and the instruments at this site, because we had the wall right here and also the gate that lets water out through Montgomery Dam. We deployed the instruments in a PVC housing that we were able to attach directly to the gate there, the wooden structure. And so the loggers are just housed in that PVC pipe there. And so now if we take a look kind of at the different deployment setups that we used for each of these sites. So at each site this past fall, we deployed 2 loggers, a conductivity logger and a dissolved oxygen logger. So both of those loggers, the one measures dissolved oxygen and the other measures conductivity, which is a measure of the different dissolved constituents in the water. And both of those also measure temperature, water temperature. And so, like I mentioned, the map on the right shows the different deployment setups that we used. So the red stars indicate the cinder block PVC pipes that we deployed in the shallower areas. And then the yellow stars indicate the buoy setups that we deployed. And then the PVC pipe is indicated by the green star at Montgomery Dam. And so for the buoys, at the sites where the water level is deeper, the water level varies depending on precipitation and also the dam operations. And so in order to capture the type of data that we want to look at the dissolved oxygen specifically 1 meter above the riverbed. And because that is where we expect the water quality conditions in terms of dissolved oxygen to be lowest. And so it kind of gives us a good baseline of what the water quality is. And we also want it to be, so we want it to be low in the water column, but we need it to be about 1 meter above the riverbed, because that eliminates any effects from sediment being stirred up. So in order to do that with the varying water level, we decided to use a system of two buoys, where one buoy is submerged about 2 meters below what the lowest water level is. And so that buoy carries the weight of the loggers and an additional weight, so that it is always, even if the water level varies, the loggers are always kept at a depth 1 meter above the riverbed. And then additionally, there's a second buoy that has a lot of slack that enables us to just locate where the loggers are in the water, and will rise and sink with the water column, but doesn't actually carry any of the load of the loggers. So that's kind of what the system that we use for the deep areas at Seabright Dam, Knowlton Street Dam, and Knox Mill Dam. And so now, just to take a closer look at some of the data that was generated from these loggers. Here, just looking at one site, Knowlton Street Dam. So this is again that 8-foot deep impoundment. And you can see in the top right, we have the buoy, a photo of the buoy setup. And so the plot on the left here is just showing temperature in green, and then dissolved oxygen in blue. And that the values for those corresponding time series are shown on the left axis, and then specific conductivity is shown in gray, and those values are shown on the right axis. And so what you can see is that we deployed the loggers in September 7th, and for dissolved oxygen and temperature, that logger was deployed from September 7th to November 2nd, and the conductivity logger was deployed from October 3rd to November 2nd. And so throughout the fall, like we would expect, water temperature in green got cooler over time related to cooler air temperatures. And then because the water temperature impacts how much oxygen water can hold, with colder water being able to hold more oxygen, we see that with the decrease in temperature, an increase in dissolved oxygen. And that within both of those time series, you can see the daily cycle of temperature and dissolved oxygen, because the loggers are measuring data at 30-minute intervals. And then you can see conductivity doesn't necessarily follow a daily cycle like temperature and dissolved oxygen, but is influenced by factors such as precipitation and other operations. So if we also take a look at how the dam operations impact the data. So what I'm showing here in yellow is the dam operations at Montgomery Dam, which is downstream of the Knowlton Street dam site. And then in orange, I'm showing the dam operations at East Dam, which is located upstream of this site. And so the orange area indicates where East Dam was opened greater than 10 inches, the gate there. So that led to a huge influx in water that was picked up at all of the sites and changed the data. So you can see in the orange figure, when East Dam was opened, it released a huge pulse of water from Megunticook Lake that led to conductivity to decrease as a result of dilution from all that fresh water coming in. And then also water temperature decreased, and subsequently dissolved oxygen also increased. And just looking at the time series of dissolved oxygen, we have shown there as on a red line the main dissolved oxygen criteria of 7 milligrams per liter, where dissolved oxygen is supposed to stay above that threshold. And we can see that for the most part at this site, it stays above that threshold, but there are a few locations early on in the time series where it's close to that threshold. So that is something that we're going to investigate further. And then specifically next year, when we deploy the loggers for a longer interval over the summer, we're going to be especially cognizant and investigate that threshold as we look at the data from the warmer months of the year, like September and August. And then back to you, Laura.
Great. Thanks, Luke. So yeah, as Luke was just saying, the monitoring we were able to do in the fall was a great first step, but a lot more data are needed for a full assessment of the river and for a more complete picture of the condition of the river. Right now, minimal historic data are available for the Megunticook River. The loggers provided a good deal of information related to the seasonal and dam operation dynamics along the river, from the most upstream reach to the most downstream, as Luke just gave an example of. We're currently moving into the next phase and developing a more robust long-term monitoring plan for the river. The monitoring plan will likely include a continuation of the loggers in the summer months, and will likely expand to include grab sampling of key parameters like nutrients, bacteria, possibly chloride. We are hoping to maybe do some rock bag deployments to monitor and assess the health of benthic macroinvertebrates in the river. We also would like to do either kick net or electrofishing survey for a fish assessment along the river, and then possibly some water level and discharge monitoring in key locations. So that information will really allow us to assess the health of each river segment and identify those that are showing any stress. These data can really help to inform restoration efforts and prioritize action in areas that may need the most help. So establishing a baseline now will allow us to track change in the river over time from forces such as climate change or other river management actions. So to wrap this up, I just wanted to reiterate some next steps in this process. So like I said, we're currently developing a monitoring plan for the river. We'll be teaming up with Maine DEP on that. And like I said, it's likely going to include logger monitoring, grab sampling, macro and fish surveys, possibly flow monitoring, to really cover the major data gaps in the river and gain a more complete picture of the river's health. And to reiterate the objective that Luke went over, it's really to establish baseline conditions for tracking change in river conditions over time. It'll help inform and prioritize restoration efforts, and we'll be able to have the data in hand to compare it to state water quality standards for DEP's assessments. Once we have a monitoring plan in place, then we can move forward and develop what we call a quality assurance project plan, otherwise termed a QAP. And that's something that's approved by EPA and Maine DEP. So that the data that we collect as part of this project is of high quality, and so that Maine DEP can use the data in their assessments. And once we have that QAP in place, we should be able to perform the monitoring in 2023 and synthesize the results, obviously depending funding availability to do the work. So that concludes our presentation. So I think I'll pass it back to Maggie and Bina if there's been any questions.
That was awesome. Thank you. There's a couple quick questions before other people chime in, but one, Luke, I thought maybe you would know. Someone was just asking what the old pipe in the middle of the West Dam outlet stream was, if you knew.
I actually do not know. And I assume it kind of runs right up to the dam, so I assume it's likely related to the dam operations. But yeah, it's kind of right in the middle of. It's actually on East Dam. Runs kind of right up to East Dam. There might be other people in this Zoom who know what that is. But definitely we'll need to follow up kind of with the town to see if they know what that is.
And then another one, just to clarify, can you guys clarify what conductivity means and whether it's a good or a bad indicator of water quality?
Yeah, I'm happy to answer that. So connectivity is measuring the ions in the water, and it's a natural component of a river system. It can be used as sort of a surrogate or a measure or an indicator of potential pollutants in the water. Connectivity would, for example, pick up chloride in the water. So if road salting is an issue near a stream, you're going to see a much higher baseline connectivity than your more natural, more rural streams that are maybe less impacted by that. Any nutrients that may be in ionic form would be picked up in stormwater and pushed to the river. So, if you had a natural river system, if you had a rain event come in with pretty clean water coming off of maybe forested land, you would typically see a dilution of connectivity, so it would go down. In an urban environment, if you have a rainstorm coming in, the connectivity would shoot up. So it really gives you a sense of the potential pollutant sources to a river.
Perfect. Hopefully that answered that question. That was great. This is a good question about, how it all factors into the big main scene, but how do these water quality measurements for the Megunticook contrast with other rivers in Maine or New England that we've measured, or, how does it stack up against other rivers that DEP has records of, maybe as a add-on to that? I don't know if we know that right now, but
I would say generally they compare well. Of course, every river system is unique, and it of course depends on size, the scale that you're dealing with. But we monitored for most of September and October, so we were a little bit late in the season. I'd really like to see the data in August, the peak growing season. That's where you're going to have the most stress on organisms. That's where your air temperatures and then your water temperatures usually are the highest, and then also where dissolved oxygen is lowest. So that really stresses out all the critters in there, especially the fish. Especially any cold water fish species. They're looking for high oxygen, cooler waters. And if they can't find that in the river system, then they're really going to suffer. They're either going to try and find small, pockets for refuge, or they're going to be forced out of the system, or unfortunately, sometimes it does result in fish kills. So we definitely want to look at that window if we can. So we were a little late this year. But generally, the river looks pretty typical for, in the upper areas where you have a little bit more of a rural influence compared to your downstream area that's clearly a little bit more urbanized and impacted by the urban areas down there.
Awesome, thanks. One question. Was any study made of the effect of the beaver community in the river on these various factors you're measuring, specifically the beaver dam between the Knowlton Dam and the Rawson Bridge?
I'll just note, Bina, I think we're going to take committee questions first. That's a public comment.
Sorry.
So maybe there's a couple hands up.
Good call. Okay, I wasn't sure. I was going through these and then I was going to go to Courtney, but okay, we'll save Charles for just a minute. Courtney, over to you.
Hi, everybody. Thanks so much for this great presentation. My first question was, can you talk a little bit about how river restoration and river health can affect marine ecosystems, especially in regards to predator prey, thinking about birds, seals, things like that. Yeah, leave it there.
Yeah, absolutely. Yeah, I can answer that, and maybe Luke can follow up a little bit too, since he has got some experience down, especially down the Chesapeake Bay estuary area, that could be relevant. So, yes, so river health is pretty intimately connected to the health of estuary or harbor systems. So in the case of the Megunticook River, you're emptying into Camden Harbor, which is pretty open to the ocean. So it's not considered an estuary, but the impact to the water quality on that system is no less significant. So what happens with the watershed land use impacts on the river, in combination with the in-river alterations that have been made, whether it's stream channel straightening or obviously, more obviously, the dams, it cuts off that connection between your freshwater areas and your coastal areas, so that fish that are trying to migrate up or out are really hitting that barrier. And then the exchange of nutrients and organic matter between those systems is really stymied as well. Obviously, also at the expense of all of the pollutant influx that is coming from developed areas, particularly in that downtown area, from the stormwater runoff. So I think maybe I'll pass it to Luke, and I hope I'm hitting your question right. But yeah, Luke, anything to add?
I think you hit most of the major points, talking about the kind of exchange of nutrients in coastal systems are largely influenced. The biogeochemical cycling, the nutrients that come in are largely influenced by runoff from land. So when you have a river like Megunticook River that's dumping a lot of nutrients, that's kind of a main nutrient source for a lot of coastal systems. So obviously any impacts that you have on land within the watershed kind of make its way all the way through down in the river into the harbor itself. So that includes pollutants. I know Camden Harbor has kind of a history of bacteria issues and has monitoring ongoing by Maine Healthy Beaches. So those they're all interconnected systems. So anything that kind of impacts within the watershed does make it down to the coastal systems. And in fact, influences the whole ecosystem, kind of like Laura described in the river. The same concept applies for marine ecosystems along the coast, where you impact the nutrient cycles, you influence the phytoplankton, the zooplankton that eat the phytoplankton and the fish, and it does eventually trickle up all the way to even seals. The whole ecosystem is all connected.
Thank you, guys. Just as a quick follow-up, I was wondering, is there any use to monitoring on the harbor or looking into data points, below the Montgomery Dam within the harbor, just to see what's going on with that system? I'm also curious about just the greater, I guess, economy, thinking about, the fisheries and the kind of the fuel we need for the lobstering industry, things like that. I know you can't really monitor that as well, but it's something to consider and think about. It's just that it's that macro view that we could take a look at, or at least discuss.
Yeah, that's a great point. We're in the midst of drafting the monitoring plan now, and we'll definitely take a look at that and probably be having discussions with DEP and possibly bringing in DMR for that, more coastal harbor monitoring. And see if we can, add a site, because I agree that it's all connected and it's all important.
Thanks,
Great. Thank you
Courtney.
very much.
Over to you, Elfie.
Hi. I'm going to go back to the thing about pervious surfaces, because I think it's a really big deal that not many people know about. And I'm wondering if what in the world communities can do about creating more pervious surfaces when roads are the way roads are and sidewalks are the way sidewalks are. Are there examples of communities that have done anything about that?
Yes, absolutely. There are, plenty of examples. That's what we call low impact development, and also green infrastructure. So it's components that are largely put into, planning documents that are then eventually adopted into ordinances at the town level to regulate, when site development plans come in front of planning boards. They have a set of criteria that they need to meet that minimizes the amount of impervious surfaces that any one development project, whether it's residential or commercial, generates as a result of that project. There's plenty of examples of new technologies that, for example, like pervious walkways, a lot of like natural vegetation that is incorporated, especially into the more urban downtown areas. Even just small changes, like if you're doing a redevelopment of an intersection in the downtown, there's a lot of designs now where they decrease, the curbing that's associated with it. They put in more plants and just reduce the amount of impervious surfaces that are associated with our projects, but still maintain the safety that's needed. So yeah, and we're happy to provide any of those examples. There's plenty of them out there, but it really has to come at the town regulatory level to institute that on new, future, and redevelopment projects.
Well, and I'll just add this one piece that our public works man, David St. Laurent, I don't know if he's on this call, but he, the town put in a little stretch of experimental pervious surface in downtown Camden, which I'm not sure if a lot of people know is there, but it's a really great experiment for us to see how it worked. But it meant replacing, it was a concerted effort to make that happen. And I don't know how easy that is to make that happen on a large scale, but I hear what you're saying. Yeah, great. Thank you.
Yeah, and I just wanted to add Laura's answer mostly focused on new development, and I know you mentioned redevelopment. It is so much harder with retrofitting existing spaces, but there are a lot of really creative engineers who have done some pretty impressive projects, even right around here in Maine, where they're making it happen, and it's pretty neat to see.
Thank you.
Yeah, great question, Elfie. Thanks. Tyler.
I have three questions, two of them with regard to dissolved oxygen. The first one is, can you guys talk about which structures within the river help increase dissolved oxygen? Do things like the dam remnants actually aid in dissolved oxygen? Or, what type of bodies of water help or diminish that?
Yeah, I'm happy to answer it, but Luke, if you want to take a stab at it.
Yeah, I can take a stab. So like you kind of said with the dam ruins, anytime you have a riffle area, a riffle zone where you're seeing kind of the frothing, the bubbling of water, you're definitely injecting a lot of water from the atmosphere into it. So structures like that, and where you have the kind of complex natural river system has those, you have the deep pools and the riffle sections in it, versus if you have kind of more stagnant water, which can be found in large deep pools or impoundments, there you're kind of getting especially in the summertime, you can get in any ponded area kind of some stratification if the water's not flowing at a rate. And so there you're kind of getting the surface water, and the deep water are cut off once you get the warm waters on the surface, kind of don't mix with the bottom waters, and you're not getting the oxygen down into the deeper part. So really fast moving water. And then anytime you can get kind of the riffling over rocks, or kind of like you said, any structures in the river can inject oxygen in the water. Anything to add to that, Laura?
No, that was perfect. Did we answer your question, Tyler?
Yeah, that was perfect. The other one with regard to dissolved oxygen was the DEP criteria line. How does that relate to any federal standards or other states?
Yeah, it's pretty typical. So the Megunticook River qualifies as what DEP calls a Class B river. And that's where the 7 milligram per liter dissolved oxygen criteria comes from. And, compared to other state agencies, it's pretty typical. It ranges anywhere from 5 to 7 milligrams per liter dissolved oxygen. Typically, the 5 milligram per liter is usually representative rivers that are what a state agency would classify as like a lower class river, something that's more impacted and can't support higher dissolved oxygen concentrations. There's also higher dissolved oxygen criteria if there are rivers that support cold water fish spawning areas. So the criteria jumps to 9 milligrams per liter between October and May, I believe.
Thank you. Last one was just, I think we saw just one chart there from your data. How did that compare to the other data loggers, or was that an average, or was that just one location?
Yeah, so that was pretty typical of at least the impounded areas. The more free-flowing areas were a little more consistent, a little less dynamic. If you remember from the figure for Knowlton that we showed, the connectivity spiked in response to some of the late fall storms, which we did see in some of the free-flowing areas, but some of those signals weren't as strong. So, but we'll be compiling this all into a brief memo and sharing all the data, and we can discuss some of the similarities and differences among the sites.
Thank you.
Just a quick note on time. We have technically 5 minutes left and a lot more questions. So I know we won't get to everyone, but I promise I'm keeping them and we'll answer them and we'll send out a follow-up to everyone. But I'm going to go to Susan Todd real quick.
Thank you. Mine are real quick and easy. One playing on Courtney's question. I just wondered why a data, or would you consider putting a data logger in Lake Megunticook as a control, or is that not something that would be considered?
No, I think, the monitoring plan that we're developing is watershed wide. So, we're definitely considering putting something in Megunticook Lake, or at the very least, including it in like grab sample monitoring, things like that.
Okay. And then my other question, which may be hard because it is the first time you've monitored this river, is were there any surprises in the data?
I don't think there was any surprises. Luke, maybe you can speak to, we might need to relocate the Montgomery Dam loggers. So as Luke showed you, they were positioned right at the gate, and it was a little bit too close to the gate. So the data loggers went a little haywire when there was a major release of the dam there, because the water was just flowing so fast that the sensors were just going a little crazy. So we might move it away from that, kind of high velocity area and just move it a little bit farther upstream or away from there so that we can collect a little bit more consistent data.
Okay, thank you.
Did you want to add anything there, Luke, or okay? Courtney, over to you real quick.
Thank you. Yeah, real quick. I've been very curious about rainfall increases over the last 100 years. It's estimated it's about 16 inches in the area, which is, you know, billions of gallons in the watershed. And I've been trying to figure out, though, how much of that water will actually flow down the river and past the dams. Is there any way to figure that out, that percentage of water that's falling in the watershed that's actually going to the river?
Sure. You know, we would have to use regional statistics based on the land cover. So what we would do is we would map the land cover in the watershed, and you know, there are local to regional what we call coefficients. So there's a difference in how much a forested piece of land can infiltrate and soak up rainfall and how much would be running off that versus, say, something that's cleared for agriculture or development, which would typically run off more water to a surface water. So we can map all of that out and use those coefficients to come up with an estimate of where the water's going to. Anything beyond that would be a little bit more of a larger research project, but those coefficients are pretty spot on in a lot of the modeling that I've done. So it's a good planning level exercise.
Okay, great. Thank you.
I guess I can also add that one thing that Laura mentioned that could be expanded as part of the monitoring plan is doing flow monitoring. And so there you'd be able to tell at whatever point of the river you decide to monitor the flow, and also look at water level. You can develop kind of a relationship between water level and flow. And then you can, if you deploy a water level logger, you can kind of continuously monitor what the water level is and get kind of an estimate for flow. And then that will tell you, if you compare that to like precipitation data that you can get at a nearby weather station that NOAA has, then you can kind of look at, okay, we better look at the relationship between the flow in the river, what the actual, how much water is actually flowing through, compare it to how much precipitation you're getting at nearby events. So you can kind of do a big data analysis in that as well.
Great.
Also through kind of modeling that Laura mentioned, so you can do both approaches.
Excellent. Thank you.
Yeah, we got a couple other questions about flooding and its impacts on sort of water quality. And I think that's all connected there, but I think we'll probably be able to answer that in a more, we'll dive into these questions more because we just hit 5:30. So I want to be really thoughtful of everyone's time and just say thank you so much to Laura and Luke for presenting. And thank you so much to everyone that joined and is watching on YouTube. This was a great, I was very impressed with the attendance. So I'll pass it over to Maggie for any final remarks, but I am logging all these questions and we will post them on the website, and we'll make sure everyone has access to that website, and we'll follow up with any further information.
I think that was a great closing, Bina. Yeah, thanks again, Laura and Luke, for the presentation. And for the public watching, we're going to work with the committee to identify a speaker every month that will hopefully kind of follow in this vein. So we're looking forward to it.
And if people have ideas for speakers, let us know, because it'd be fun to hear diverse thoughts on who we should have. But thanks again.
Great. Well, have a great evening, everyone. Thanks for joining.
Thank you.
Bina,